Hey physicists, welcome to Standard 5.3. In this video, we're going to talk a little bit about the definition of work, which is kind of the big topic for this standard. Before we do that, though, I want to remind you a little bit about what 5.2 was focused on, because that'll give us some context for why we're talking about the things in 5. So in 5.2, we focused on the concept of conservation of energy. And conservation of energy basically said that the total energy at one point in a system needs to equal the total energy at another point in the system, provided that the system is closed. So I'm going to say within a closed system. And that's a big if. That's a big thing that has to be true in order for conservation of energy to be able to be applied. And the idea of a closed system basically means that there are no outside forces acting. So anything that is interacting in that system has to be part of the system itself. That works really well, again, when you're talking about a closed system. Standard 5.3 focuses on the kind of opposite, the rest of the situations. So that would be things where we have an open system, right? Situations when we have outside forces acting. So that could be a push or a pull that's making something get faster. It could be something slowing down an object. It could be something lifting an object up and changing its energy. In any of these cases, the game is that conservation of energy doesn't really hold anymore, okay? Those outside forces are going to add or remove energy from the system, okay? Now, there will be a video later on in this module that talks about removing the energy in a little bit more detail. So today we're going to focus mostly on adding energy to a system. And we add energy to a system by doing something we call work. You've heard of work. You do work all the time. But there is a very specific definition for work when it comes to our physics situation. And work, which is marked with a capital W, really means something that is changing the energy within a system. Now, how might you change the energy in a system? Well, it's kind of sitting right here in front of us. It's by applying a force, okay? So work is done when you apply a force to an object or to a system of objects, okay, over a distance. Now, this definition has a couple of little details in it that we're going to get into through some examples, but this is the fundamental piece of it. Before I do those examples, so I just want to point out here, just looking at units so that we don't get confused or bogged down later. We know the unit of energy, it's a joule. If work is also equal to the change in energy, then that means that the units for work are also a joule, which again is a capital J. Okay. So I've got 3 examples here to look at with you so that we can analyze kind of what's going on in these work problems. They all involve food. I hope that you are not sitting here on an empty stomach. And I'll explain why here really quickly. So the first question, and this is kind of where they all were born out of, is about lifting a cheeseburger. Now, you might be like, why a cheeseburger, Miss Carveling? Well, let me tell you. The reason is I saw it in an example somewhere lots of years ago. But if you think about a cheeseburger, right, like a quarter pounder with cheese, for example, that has a or a weight of a quarter pound. We can kind of conceptualize what a quarter pound is. It just so happens that a quarter pound is about 1 Newton. And so now we've got a nice equivalency here. We've been talking about newtons for a long time, but to get a sense of really what that means, if you can imagine a quarter pound cheeseburger, that has the weight of 1 Newton. Okay, so now what are we going to do with the cheeseburger? We're not just going to let it sit. No. We're going to take it from our plate and lift it up towards our mouths. So here is my cheeseburger, and I don't want to be leaving anybody out. So if you are lactose intolerant, then make this a hamburger. If you are vegetarian or vegan, then make it a veggie burger. If you don't eat gluten, then just make it a piece of meat or something else on a plate. But it's going to be something that you're going to lift up from the table to your mouth. So here's the table, and there's the cheeseburger. And in order to eat it, we're going to lift it up from the plate to our mouth. So we're going to lift it up some distance from here up, and I'm going to mark this as D. I know that sometimes in physics we use like a delta Y or a delta X, but for some reason when talking about work, generally we call it a distance D. Now, if we're going to lift it up, we have to apply a force to it, don't we? Yeah, we're going to apply a force, an outside force to the system. So what is the system? Well, we can kind of define that. That's going to be the cheeseburger and maybe the plate or the table, but really we're talking the cheeseburger. And then of course, we've got the earth involved as well, okay? We can decide where our h equals 0 point is. Generally, I want to keep that as simple as possible. So I'm going to go ahead and make my h equals 0 right where my cheeseburger is. I'm not the best artist in the world, so you have to forgive me there. But there's my h equals 0 point. So at the point before I've lifted the cheeseburger, we're at our height equals 0 point. Now, we need to apply a force, don't we? We're going to apply a force to lift our cheeseburger, and it's going to lift up. So we're going to apply a force in the upward direction. How big is the force? Well, if you're going to lift the cheeseburger at about a constant rate, that means that the net force acting on the cheeseburger needs to be 0. So I'm going to apply there's a gravitational force, the earth pulling on the cheeseburger downward, and I'm going to say that my applied force is the same size, so that I'm lifting it up at a constant rate. Okay, so I've got an outside force acting on my cheeseburger, lifting it up a distance d. So now we can figure out how much work is done. We have that equation, that statement from the prior page, and we can say that it's the force times the distance. We have a force of 1 Newton being applied over a distance of, oh, I don't know, depends on how tall you are, depends on how high the table is. Maybe we'll say that the distance is, let's say it's 40 centimeters. So that's going to be 0.4 meters. So we've got 0.4 meters. And just purely doing the math, we can figure out then that we do how much work? It's 0.4 joules. Okay, so actually plugging it in, not a big deal. Let's look at it in terms of the bar chart scenario that we talked about during 5.2 as well. So let's look at our kinds of energy. Prior to lifting it up, the cheeseburger has no kinetic energy. Given where we set h equals 0 at the beginning, it has no gravitational energy. There are no springs, there's no elastic involved, so the elastic energy is 0, and also no thermal energy. So at the beginning, when the cheeseburger is just sitting there on the table, in terms of the energies that we're talking about, there is no energy in that system. Now we're going to lift that cheeseburger up, we're going to do some work on it, and at the end, it's going to be way up here, right? Right up there. I'll put some sort of something in the middle there. There's your cheeseburger now. It is now some distance away from the h equals 0 point. So now it's got some gravitational potential energy. How much? I don't really know. I'm going to decide it's 3 bars. Okay? I stopped it there at the top, so there's no kinetic energy. Again, no elastic, no thermal energy. So my bar chart is pretty straightforward, but it doesn't fit that conservation of energy statement that we were doing in 5.2. Oh, no, it doesn't, because work has been done to the system. And so now we need to document that within our bar chart. How do we do that? Well, I'm going to show that by an arrow, okay? That arrow represents the work being added, or energy being added to the system through work. So I'm going to go ahead and write that down. There is work done, and the work is done by an outside force. It's an applied force. And you might even want to write down that it was by my hand or by your hand as we lift that cheeseburger up. And then finally, we need to know how much energy has been added to the system. So we have 0 bars over here, right? There's no energy. And then over here, oops, come on, there it goes. It was doing great. There we go. We've got 3 bars, which means that we had to add 3 bars of energy, right? Now, does it have to be 3? No, but whatever this says right here needs to match the change from the initial to the final. Okay? one last piece just to kind of put this all together to make sure that it makes sense as you're thinking about it. Remember on the last page, we had said that there were two definitions for work. We said that work was equal to force times distance. We also said that work was equal to change in energy. So I'm going to write this out as a kind of a conservation of energy statement with that change in energy in there as well. I'm going to say that the total energy at the beginning, I'm going to go ahead and call these initial and final, plus this work is going to be equal to the total energy at the end. Okay? That's really what we're saying here, is that now the initial and final don't necessarily equal each other. We've got that work piece in there as well. So if we add these together here, I'm just going to throw some more ideas at it. Maybe there was some gravitational potential energy at the beginning. Maybe not. In this case, we said no, but we'll just go ahead and leave it like that. Plus, well, that work was a force that was acting over a distance, okay, equals mgh final. Now, we called mgh initial 0, but I'm just going to leave that in there. The force that we applied was the same as the force of gravity, so that's really just mg. And that d really is a change in height, okay, is equal to mgh final. There's mgh initial. And so we can see from this, if we look at it in a clever way here, the mg's are going to go away. So really what this is just saying is that our initial height plus our change in height is our final height. Okay? This right here is just a nice, neat, easy way to show that the work is the change in energy of the system. Okay, two more quick examples to kind of put all of this together. The second one, again, involves food. So, there's that. This one involves carrying a pizza. Now, I've never been a member of a wait staff at a restaurant, but I've certainly had pizzas delivered to me via a waiter or waitress. And so I've seen this happen before. So here's the pan that my super yummy pizza is on. Maybe there's some sauce on it, whatever. Okay, but I'm imagining right now the part where they're carrying the pizza. So they dinged the bell at the kitchen, and now they're going to carry that pizza out to me. And in doing so, the waiter or waitress applies a force upward to keep the pizza from falling, right? As they walk, there's of course gravitational force pulling down. And assuming that the pizza doesn't accelerate up or down, well, these two forces have to be the same, just like they were before. Now, as we said, the pizza is going to be moving some distance d like this, and there you go. That's the scenario that we're talking about. In this case, my question is, how much work is being done? Well, there's a force, right? There's a force that's applied right here to my system. My system is what? It's a pizza, and it's maybe the pan as well, and the earth. The person carrying the pizza is not part of my system. That's an outside force acting, okay? But as that person is carrying the pizza, are they doing any work? So remember we said that work is equal to the change in energy. Now, I'm going to assume for this scenario and for this story that the person carries the pizza with a constant velocity. The acceleration with which they move at the very beginning and then at the very end to slow down when they get to your table are kind of some end values. And there's a little bit more interesting stuff that happens there, but we're not going to get into that. If they're moving it at a constant velocity, then let's say that we've got some kinetic energy. Sure we do, right? Because it's moving, so that's good. We've got some kinetic energy to start. But as that person walks, it's going to maintain the same kinetic energy because it's got the same velocity. Is there any gravitational potential energy? Sure, unless they're walking it along the ground. Or if you set h equals 0 at the height of the pizza, then I guess there would be no. But let's just for kicks, let's say that h equals 0 way down here. Then sure, there's some gravitational potential energy. And there is here too, okay? Gravitational energy is the same in both cases. As was true in those first two, the first example as well, no elastic, no thermal. So if we take a look at this, there's no change in energy in this system, okay? It doesn't speed up or slow down. It doesn't move up or down. So even though there's a force acting and it's moving, there is no work being done. You say, but Miss K, earlier we said that work was also equal to force times distance. And I did, but remember I said that there was something a little bit different. Now, if you look at your equation sheet, or if you look at in the book, the way that the work equation is written down, it actually says F times D times the cosine of theta. Now, for some of my friends, that's no big deal. Some people are like, oh, because cosines seem really scary. So I'm going to tell you my version of this as well. I like to say that work is equal to force times distance, where the force and the distance have to be parallel. So let me tell you a little bit more about what that means. If the force is parallel to the distance, like it was in the scenario of lifting up the cheeseburger, right? The force is right here, the distance is right here, they're in the same direction, then work is done to the system. Work is done, energy, let's say we have a positive change in energy, okay? If the force is anti-parallel to the distance, what does that mean? It means that the force goes in one direction and the displacement or the distance goes in the other direction. Then we could say that negative work is done, maybe. Oops, negative. So when I think about this, I think about, like a car that's driving and then you put the brakes on. Putting the brakes on means a force is going backwards while the car is still moving forwards. In this kind of scenario, we have negative change in energy, something like it's slowing down, okay? In those cases, we both still have a change in energy and there is still work. But, and this is the one that really matters, if the force is perpendicular to the distance, there is no work done. Even if there's a force applied, okay? If the force and the distance are perpendicular, there is no work done. So that covers most of the scenarios that we're going to deal with. But I know that I've got a few people out there going, but wait, what if I have a force that's acting at an angle like this while there's a displacement like this? Good question. If that's the case, you will break that force into two pieces, one going in this direction and then one going in this direction. And the only part of the force that matters is this part right here, okay? You will not in this class have to do components. You won't have to actually break those down numerically, but I do want you to be aware of this case, okay? Because that is really important. All right, last problem, and then we will be done with this lesson. Last one. This one more time, involves food. Something that I imagine you all never did, but I have a young person at home that is often tempted to do this. Let's say that there is a table, and on that table, my young person at home was served something that she was not such a fan of, like maybe some sort of blue goop that seemed really off-putting, okay? So if that's the case, it might happen that she would push that plate away. Not so excited about eating blue goop today, Mom. Applying a force, FA, in that direction. Now, to keep things simple, we're going to assume that there's no friction on the table because that gets a little more complicated. Other forces acting on that plate, well, of course, we've got the force of gravity, the force of the earth acting on the plate, and we've got the normal force, the force of the table acting on the plate. Those two are equal. There is an applied force, an outside force in this system, the system being the plate with the goop, okay? And then we've got the earth, of course, maybe the table too. We're assuming again that the table has no friction just to make our life a little bit easier. In this case, we're going to displace that goop a little ways like this. So there's some distance. Here's the distance. There's a force. There's the force. The force and the distance are indeed in the same direction. They are parallel to one another. So we can say that the work is equal to the force times the distance. They are parallel. I'm going to mark that just so I don't forget. And what kind of a change in energy is that making happen? Well, if I call H equals 0 here, then my gravitational potential energy is 0 in both cases. My elastic and thermal potential energies are also 0. Assuming that there's no friction, I'm going to start off with no energy to start, okay? And then as she pushes it, it's going to accelerate. We're gaining energy. Wait, we're gaining energy? What? No, no, no. I mean, we are, but the energy we're gaining comes from work. We're not breaking any physics laws. We are using the work energy theorem here. So there is work done by an applied force, maybe from the hand or something like that, and that adds, in this case, 2 bars of energy. So those are 3 pretty simple examples, but hopefully they help to start that process for you. Have a great day, you guys.